computer. Hello and welcome to our 6th week of class. Can you believe it's already 6 weeks in class? Anyway, so what we're going to do this week is we're going to start proton NMR. I'm going to do a lot of theory, especially today. And then as we go with, I'll also add in the tables and how to use them in the book. And then we'll start going ahead and taking IR, mass spec, and proton NMR and getting a more refined structure from each of the different components. The different components will give us different things, you know, empirical formula, functional groups, and then NMR is going to give us that last bit of information, connectivity. Now, proton NMR won't tell us everything, which is why we have other NMR techniques to use. However, this will get us to a lot of the simpler problems where connectivity can be just found by shift and or coupling. And so we'll talk about that. But sometimes shift and coupling doesn't answer our questions, and we have to go even deeper. So that's why we're going to do carbon-13, we're going to do 2D NMR, and then we might even get to other nuclei if I can get to them this year. Okay, so that being said, due this week, it's just lecture. We'll have an activity, an NMR activity for lab next week. I'm sorry, in class next week. And then also the homework for NMR chapter 3 will be due Friday of next week. So that will be, so it's just kind of lecture this week and figuring out how to use our tables, etc. Okay, so according to our tentative schedule here, we have NMR for today and Thursday. And then our activity will be on Thursday the 8th of next week. And we'll, by Thursday, we'll be doing a lot of practice of problems. And by the following day, it'll be just, you know, really hard NMR problems and how to solve them. Okay. And then, of course, we'll have our next exam, which will cover mass spec, IR, and NMR. And then we'll switch into carbon-13. Okay, so that being said, any questions about administration right now? Okay, so I'm gonna go ahead and pull up my slides and we can start talking about what we're doing today. Again, the Zoom chat is open if you wanna ask a question that way. And let me go to share with my iPad. All right. I hope you all see my slides here. This is the book we're using, 8th edition, but okay, let me move the gallery mode up here. There we go. There we go. Still, oops, shrink. There we go. All right, so there we go. So we're going to do proton NMR, but in general, I'm going to talk about NMR as a technique first and how you can use different nuclei to do this. But we will then focus on proton NMR because that is where our shifts and our splittings are going to happen for this particular thing. So I've broken this into 3 parts. One is just the introduction. The second is going to be problem-solving techniques. The third is going to be problems. So let's go on to talk about nuclear magnetic resonance spectroscopy, or more lovingly known as NMR. And basically, we're looking at the radio frequency of the electromagnetic spectrum with a twist. Well, technically it's a spin, but we'll talk about that in a minute as well. Now, most of the time this is observed in a very high magnetic field. And the reason we do this is we need to have things aligned, knock them out of alignment, and then listen for them to come back into alignment. And so that's how we're actually observing these things happening, okay? So some important factors about actually how we do NMR experiments has to do with nuclear spin, and I'll talk about what nuclear spin is and why we have it. Isotopic abundance, okay? In addition to isotopic abundance, we also have what's called susceptibility. So some things are easily knocked out of precession, some things aren't, okay? And those are related. Then we have nuclear mass, okay? The mass of the nucleus also makes it harder to knock out of precession. And then we have peak shifts. Peak shifts are moving up and down the spectrum based on how shielded they are by their electrons or how not shielded they are by their electrons. And we'll talk about all these different factors and how they get into what we're looking for in an actual NMR spectrum. Okay. So the first, if you upload it early, you might not have the slide, but it's just an example slide. So when we talked about IR, we were talking about this region here, and we were talking about how it was the vibrational spectroscopy, okay? So we have an energy that can be absorbed that causes the two atoms to vibrate and have a frequency, occasionally three atoms to have a twisting or bending, okay? Now, if we go higher energy than that, we can go into electronics here. And this is UV vis. And if I have chance, I'm gonna do one lecture on UV vis because there's some interesting stuff here. And what this is about taking an electron from your pi cloud and putting it into your unoccupied level. And so that is an actual electron excitation, okay? But we're gonna go to the complete other end of the spectrum here, and we're gonna talk about radio frequency. Now, radio frequency, because they're so long and they have such long frequency lengths here, we end up looking at the magnetism of the nucleus. So every wave has an electronic and magnetic component. As they get to these long waves, it's a time frequency that allows that wave to interact with the magnetic moment of a spinning nucleus. And that's where we're going to be talking about our stuff today. So we actually have 3 different bands in which we look for information as to our chemical compounds. And they all affect different parts of the different chemical compounds. So we have 2 atoms, we have an electronic state, and we also have the nucleus. Okay. So let's talk about the nucleus. Okay, just like a planet, a nucleus typically has a spin to it and an axis. And so it spins on this axis, and just like this, it has angular momentum, okay? And when we think about this, it then has a charge associated with it. And this is related to that angular momentum, and it can be 0, 1/2, and any integer or half integer there. It can only be 1/2, 1, 0, you know, so it can't be some 0.33 number or anything like that. Okay, so we have our spinning right here, which has our magnetic moment. Then we have our angular momentum here that we're looking at. Okay, so each nucleus, not just the actual proton or neutron in the nucleus, it's the entire nucleus itself is spinning. Okay, so where do we get the actual nuclear spin generated by the collection of neutrons and protons in that nucleus? Well, it turns out we have to go below, or a subatomic particle. We have to look at the quarks associated with it. So in a neutron, we actually have the -e third charge of 2 of the quarks, and then a +2e charge on the third quark, which gives us a net half value, okay? Now, with the proton, we actually have 2 of the 2e third spins and 1 of the -e spins, which gives it a net 1/2 spin as well. So the neutron has a half spin and the proton has a half spin, okay? So if we have 1 neutron and 1 proton, they can cancel each other out because one will be a spin up, one will be a spin down, and they'll cancel each other out, giving us no spin. Okay, we don't have to go counting quarks in our nuclei to figure out this. We have a simple tool for us to use, and it's called the odd-even rule, okay? So if you have an atomic number, i.e., you know, your atomic number is based on the atom, so carbon is 6, so that's an even number. Hydrogen is 1, that's an odd number. So that's the atomic number on the periodic table, okay? If you have an odd atomic number and an odd atomic mass, that means you have a mismatch between protons and neutrons, and therefore you have spin, okay? In this case, when we have these odd configurations, we can have half spin, okay? Because you can never balance the proton and neutrons, so they always have half spin. And so luckily, we have a lot of nuclei that do this. And the one of most interest today is, of course, hydrogen, which is the most abundant isotope of hydrogen we have. There's also tritium, which also has a half spin here. So you add 2 neutrons to it, now there's still a mismatch, and you have a half spin. Certain isotopes of nitrogen, this is not a very high isotope of nitrogen, but it does have half spin. But cool thing is, fluorine has 1 isotope and it has half spin. So that means we can do fluorine NMR quite easily because it has a high concentration of that particular isotope. We can also do it with something like phosphorus. Okay. Now, let's go to what if we have an even number like carbon or oxygen or silicon. Okay. If you have an odd atomic mass, you can still have a mismatch between protons and neutrons, and you get a half spin. Okay. So that mismatch in carbon-13, which is only found in 1.1% of carbon, but it's enough that we can see it and do NMR. And we'll talk about that in the next chapter. However, again, because we have a mismatch between protons and neutrons, we get half spin for one of the isotopes of oxygen and one of the isotopes for silicon. Okay. Now, if we go to the idea that we have an odd atomic number, but we have an even atomic mass, that means that we're going to have a balance between neutrons and protons, and we're going to end up with a spin that's an integer. Okay. So in the case of deuterium, or the primary isotope of nitrogen, we have a spin of 1. Now, there's an odd quantum mechanical derivation that makes boron actually have a spin of 3. Okay. And we can take that to our advantage when we do boron 11 NMR, which I might get to, which it'll have 3 half spin, because it'll have that 3 spin that's an integer, which we can't see, but it'll have an additional half spin because of the offset, and we can see it. Okay. So that's one of those weird ones. And then we have the possibility of having 0 spin. And that's where we have an even atomic number and an even atomic mass, meaning protons and neutrons are exactly equal to each other, and they cancel each other out, and we have 0 nuclear spin. Okay, so the most common ones that we're going to deal with are what we call the half integers that are odd atomic number and odd atomic mass, and the ones that are even atomic number, odd atomic mass. Each of these will give us 1 half spin, and those are the primary ones we do NMR on. Questions on spin? Okay, all right. So now that we know that all these nuclei have spin, and in their standard state, you have this nuclei, and it's spinning around, and it's got its magnetic, moment that it has, and it has this angular momentum as it's spinning around. So if you can imagine, this finger is spinning around with the angular momentum, and this is the direction it's pointing in. Okay, if it's just by itself, the difference, the energy state that it has is pretty modest, because there's no external magnetic field interacting with this. Okay, now if you apply an external magnetic field such that this is having to get out of that natural state, we now have a possibility of spin with the magnetic field or against the magnetic field. As that magnetic field gets stronger and stronger and stronger, the difference in energy between with and opposite gets bigger and bigger. Okay, so that means we have 2 different energy states once we are able to pulse it with that radio frequency. So the greater the field, the greater the distance, the greater the energy distance, the easier it is to see the change that we see when we excite these nuclei. Okay, so if you have a very high field magnet, you can use less frequency. If you have a low field magnet, you need more frequency. But at our university, we have a very high field magnet and a very high frequency. So we are getting that difference as great as possible, and we get greater resolution because of that. Okay. All right. So that being said, let's talk about that nuclei. Okay. So we have our spinning proton, and it's spinning around, and so it has this nuclear magnetic dipole, and it's just kind of sitting there, and it has this angular momentum piece going around it as it's spinning. Okay. Now, just like the Earth, they don't spin on this axis and stay there. They actually have what's called precession. Precession is where a spinning top will start to rotate slowly around that axis, okay? And there's a stable portion for this. So you could imagine a top, if it's spinning and doesn't slow down, it's going to keep that precession as long as it can, as long as it's retaining that angular momentum, okay? So we have this precession here, and that is a normal thing that it has. And it usually aligns with that magnetic field, but it never aligns completely, so it doesn't have precession. You don't have it just strictly there. It always has a little bit of precession, and that precessional orbit changes with the mass of the nucleus. Okay. Okay. So if we can imagine where, take a snapshot of the magnetic moment as this thing is progressing around, we're going to see there's one where the magnetic moment's here, and then it's here, and then it's here, and then it's here. So if we added up all the magnetic components of this, we would end up with them being aligned with our magnetic field, okay? And so that's our net direction is going to be in that magnetic field direction. However, it's not ever always 100% there. It's usually somewhere around that. So what this means is that we have a frequency that we can hit this with that will match that to give us resonance, okay? And by using a frequency to find that resonance, we can learn something about the state of that thing. So in this case, the energy absorbed by the proton is promoted to a higher energy state. And guess what? When it's in that higher energy state, it's kicked out of that precession that it would naturally be. Okay. So let's hit it with RF field here. So we have our rotating proton in our magnetic field here, okay? So it's got its little precession going, and then we hit it at a right angle with an RF field, radio frequency field. So the first thing it's going to do is it's going to knock that magnetic moment out of its current precession, and it's going to knock it off closer to the XY plane, you know, because it's hitting it perpendicular. So now that it's over here, it's still trying to realign with the magnetic field, okay? So that path it takes as it precesses back to that magnetic field is the time it takes to go from that excited state out of the magnetic field back into the ground state. And there's two processes associated with it. First is just the actual coming back to the precession, and then there's this spin is reacting with a spin nearby, and these have a different time regime. So we have our first time regime called T1 is just related to the nucleus, and the second one is the spin-spin. So again, this spinning proton and this spinning proton, even in the same nucleus, has a coupling associated with it. And so what we get from that is we get what we call a T1 relaxation, which is the spin, or getting back to that alignment. And then we have the spin-spin, where this is usually different, and therefore we can actually tell some experiments about this. When we get to other 2D experiments, we actually do what's called a 2T experiment, a T2 experiment. And that tells us a lot more about how they couple together, and that gives us additional information about the species. The most important one we're going to be talking about in proton NMR tends to be the T1, and this gives us a lot about the intensity of the peaks that we get here. With the T2, we actually end up seeing that if the T2 is short, then this happens very quickly, and we have very few scans that see it out of alignment. But if it takes a long time for this T2 to relax, we see that the line's broaden, okay? So the idea is if you have a very short T2 and a longer T1, you get less broad, more intense peaks. And so they get sharper and more intense. So those are the two processes that are happening after you hit this with radio frequencies. Okay, questions about that? So the idea is that you've hit it with radio frequency, and now you're waiting for it to get back. And that time difference between the two tells you a lot about the electronic shielding around that proton. So what does that look like to the machine? Okay, so in our sequence here, what we do is we have our, oh, that's, okay, sorry, I heard a noise. It was my daughter out there. Anyway, so we have our, in our magnetic field, we hit it, right? And so some of the nuclei are coming back faster. Some of them are, let's say we have one that's just a methyl group, the hydrogen on a methyl group. It comes back fairly quickly, okay? And then we have other ones that are maybe hooked to a benzene ring. They come back slower, okay? So if we look at this diagram right here, we have some of the signal coming from one part of this time delay. So this is 0.1 seconds after our pulse, and now we're waiting for that precession to come back into alignment with our magnetic field. So we're getting some signals from some of those protons, and then we're getting some signals from other protons, and we're getting some signals from other protons, okay? Because they all relax at different times. So we're looking at those different relaxation times. However, we can't really kind of read this spectrum here, you know, and seeing what it is. So what we do is a mathematical derivation called the Fourier transform. And what that does is that takes our frequency domain and turns it into a physical domain. And so when we take this whole spectrum and do a math and add all these together, saying, okay, this plus component adds to this plus component, adds to this plus component, this minus component adds to this minus component, to this minus component. We end up getting all of our minus components and all of our plus components that cancel out, turn into our baseline. Things that don't cancel out become our peaks that we see, okay? So in a simple one peak system, you might see, oh, that's very consistent, a nice harmonic looking spectrum. But then as you put in different types of protons, they're going to have different relaxation times, and your peaks get a lot more convoluted, okay? So obviously we definitely need to use a computer to convert from this free induction decay, or just the actual looking at all the frequencies as they decay and converting it into something we can use, okay? So I don't know if our NMR does this or not, but when we first got an NMR, we were taught to actually listen for the ping when you locked in on your spectrum, because it would go ping, ping. That means you weren't kind of locked in, and so you wait for it and you go ping. That means you were focused in on the frequency, and that was basically an auditory version of this FID. We could actually hear it go ping. And then that would tell you you were focused right on your thing. So I don't know if they show you FIDs on these anymore. It probably just says locked or unlocked, but this is, you know, this is really what's happening in the background on the computer. Okay. So obviously we can't translate that with our heads, so we use the Fourier transform. And so that's a mathematical convolution where it takes a frequency domain and converts all of those different pulse sequences into a readable spectrum. And so, I'm sorry, it takes it from a time domain into the frequency domain, okay? And so obviously frequency is over time. And so it does this mathematical convolution. I've never done one before. I hear they're very difficult, but we let the computers do it. So once we do this, that gives us the spectrum that we look at and try to figure out where all of our different nuclei are on our system. Okay, so most of you have probably used the NMR up at Texas State, right? Okay, so there's some little things that you might not see. You know, obviously you see the computer and you've done where you've added your sample to the top here. And some of you may even know that there's a liquid nitrogen doer and a liquid helium doer. So the liquid helium doer is at 4K. And the reason it's there is because the primary magnet used to create the high magnetic field is actually a superconducting magnet. And it has to be kept at 4 Kelvin to get it to go. Now, to keep the helium from boiling off too quickly, they encapsulate that with a liquid nitrogen doer, so it boils off slower. So that means our primary magnet in here is at a fixed field and at a fixed strength. Okay. However, because of you know the microstructure of the magnet here, it's not necessarily a homogeneous field. And that's what we have magnetic coils for. The magnetic coils help make the field more homogeneous, more straight in line. So ideally, you want your field to be 100% parallel inside that sample chamber. Okay, that way you're getting all of your nuclei aligned in that same field. And the more homogeneous that field is, the cleaner a signal you'll get. Okay, so then the next thing we have are what are called CHEM coils. And that's what you use when you actually put your sample in there to try to get it aligned with any anomaly you have in your sample. Now, one of the things we do for homogeneity, so our magnetic field is trying to be homogeneous, and to get our sample to be homogeneous, that's why we spin it, okay? And so that's why you spin a liquid sample, because that gets it as homogeneous as possible in that field, okay? So that's what's happening inside the big doer here. And then, of course, there's the probe. And the probe is basically coils that sit on either side of that. And one of them has the transmitter that pulses at a right angle to your sample and the right angle to the magnetic field. And the other part of the probe is the part that listens for the response. Okay, so there's the emitter and then the part that just listens for the response. Okay. So these right here control your magnetic field. These right here actually do the pulse and listen to the system. Now, once everything's set up and going, you go ahead and run it through and your computer spits out this perfect thing. Now, notice this thing over here. This is your pulse generator, okay? With Proton NMR, we have a specific pulse sequence. It pulses for 1 second, waits for 10 seconds, or waits for 1 second, and then it pulses again. Okay, so that's the pulse sequence for Proton NMR because it's 99% hydrogen 1, which is spin active. Okay, however, for carbon 13, it relaxes slower. So we actually have a different pulse sequence. It pulses for 2 seconds, waits for 10 seconds, and listens for that relaxation. Okay, so that pulse generator has to be able to do different pulses, different frequencies, and different time delays to get you the information you need. Now, also with our pulse frequencies here, you can actually do 2 pulses. For example, when we do a decoupled carbon NMR, it pulses 1 frequency to take the hydrogens out of it, and then pulses for the carbon. And so these hydrogens are busy while it's listening for the carbon, and that's how we can decouple from those. And that's a different pulse sequence experiment. And I'll talk about that more in our carbon NMR section, okay? So luckily for you, it's very easy that you just push the button. But this is what's happening in the background. And so there's a lot of people out there who come up with these cool new pulse sequences. In fact, I have a book sitting around on the shelf there. It's called 200 NMR Experiments. And it's changing your pulse sequence, changing your delay sequence. And so you can get 1, 2, 3D NMR, multiple nuclei, and it all have different frequencies and things. So there's a lot that our NMR can do that we don't actually use it for a lot of the time. Okay. So let's talk about sensitivity. To get a good NMR spectrum, you need to have a good signal to noise ratio. That's what S/N stands for. Okay. And so in our NMR, we look at it from the point of view of our field strength as well as our number of scans. Okay. So the first thing that accounts for this is the number of spins in the system. Okay. Which means the number of protons, in this case, hydrogen atoms in there. That means it's directly related to sample concentration. Okay. Now, if you can load up your sample until it starts to become viscous, that's great, because the more number of spins you have in the system without affecting the homogeneity. So if you start changing the viscosity, you are going to change the homogeneity. So as high a concentration as you get without changing the viscosity is a good thing. Okay, then we look at our T2, our transverse relaxation time, our spin-spin interference between spins, okay? So hopefully that's very short and we can get rid of that. But then we have our magnetogyric ratio of our excited nuclei. So these are the nuclei that actually get knocked out of the magnetic field. And the magnetogyric ratio is the ratio between the magnetic moment and the angular momentum. So if the ratio of this is fixed for most of the different nuclei, so you have the moment here and then the angular momentum, magnetic angular momentum associated. Okay, then that's all next to the cube root of the external field strength. So the higher that external field strength, the more sensitive the NMR is going to be. And then it's by the detected nuclei. So that's the magnetic ratio of the ones that are actually being detected by the sensor. Okay? And then we have the square root of the number of scans. And temperature does play a role. It does change relaxation time slightly. And so temperature is controlled in these experiments as well. Notice that it's a square root, so it's a lot of times you'll be restricted to things like 16 or 64 to make it easier to do a square root of. If you have an odd number there, that really kind of messes with your Fourier transform. Okay, so any questions about that? So basically, major effects are the relaxation time, the magnetogyric ratio, and the concentration. Okay. All right. So now that we have our nuclei, we're in solution, we're pulsing them, we're knocking them out, and then we're waiting for them to come back. Okay. And those two time regimes give us that, that decay spectrum that we can translate. Now let's talk about what changes the time at which it takes to come back. Okay. And when we convert that time domain into that frequency domain, that equates to chemical shift. So if it didn't take very much time at all, it's going to start at a very low number. And the longer it takes, the longer it takes, the more it's going to be shifted downfield. Okay. So chemical shift is the difference between the absorbed frequency of a particular set of nuclei and its reference. We typically use tetramethylsilane as our zero. One of the reasons we want to know that is because if you change field strengths and or frequencies, you don't know exactly where zero is. And so by always including your tetramethylsilane, you will always know where zero is, and you can always measure out from that. Okay. So with knowing where zero is, now we're looking for protons again, hydrogen. And so the rate at which it comes back into alignment has to do with how much of the magnetic field it can see. Now, if it has electrons around it, a higher concentration of electrons around it that have their own magnetic fields, you can shield the nucleus from that magnetic field. So if you're shielding that nucleus from the magnetic field, it actually takes it shifts it from one part of the spectrum to the other. As these electrons are pulled away from that nucleus and the magnetic field can see the nucleus more, it becomes de-shielded and we shift upfield. Okay, so it's all about the electron configuration surrounding that hydrogen that tells us that. Now, what tells us how much electron density is around there? It's what it's attached to and what's so example, if you have a non-polar bond, you're going to have a fixed amount of shielding on there. If you add something that has a pi bond, that's going to shift, that's going to de-shield it, that's going to make it change time domains. Okay, and we'll talk about that as well. But it's just the idea that the electrons are why we have these shifts in this spectrum. Okay, so go ahead and look in your book at chart A1. Okay, so this is a crazy, crazy chart, okay? But let me show you how to use it, okay? So the idea here is that these are where we expect the hydrogens displayed to show up on different functional groups. So if we look at our table here on our book, let's look at the first one here. and it's the M, which is a methyl group next to a CH2 and the R, okay? So what this is saying is that a methyl group attached to a CH2 is going to show up at approximately 0.8 ppm, okay? Now, that means a methyl group. That's a carbon with 3 hydrogens on it. If you had a carbon with 2 hydrogens on it, that's going to be the 2 open dots. Notice that's shifted up to 1.2, okay? So those 2 hydrogens that are on that carbon now have shifted up to 1.2. And if we only had 1 hydrogen on that carbon, where it's attached where the M is, that's a methine, okay? So that's where you have 1 hydrogen, and it's shifted above. So in the case where you have a carbon attached to a CH2, if it's a methyl group, it'll be the first one, a methylene or 2 hydrogens, the second one, or methine, 1 hydrogen, the third one. So, excuse me. So that's how we use this chart, okay? So let's go down and look at something else. Let's look at MOH right here, which means that methanol should be the one with the bar. So the methanol methyls should show up here at 3.2, okay? Let's say you had something attached to that methane so that it only has 2 hydrogens on it. That's going to be shifted up to this 2.4, 3.4. And if you only ended up right here, well, you had like isopropyl group here, it's going to be shifted up to this 3.8, okay? Does everybody see how to use that table? Okay, so you want to look for the number of hydrogens on your position of interest and then look at what's connected to it, okay? So that's the first thing to use. And this goes good if you have nice, simple ones with only 1 functional group attached, okay? And obviously, I don't want to go through all of these, but as you get used to it, you'll see the different functional groups. You'll start recognizing the functional groups and their shifts. Okay, so let's go to what we mean by shielding and deshielding, okay? So different NMRs have different frequencies at which they use. The bigger the frequency, the greater the distance between, remember, as that field increases, the energy difference between half spin and half spin plus, half spin minus gets greater, which means that our frequency actually gets bigger and bigger. So what we do is we account for that by converting our frequency of our NMR into the ppm scale. When we do that, it doesn't matter what frequency your NMR was. The ppm scale has already taken into account the frequency, and therefore 10 ppm on a 50 megahertz NMR is 10 ppm on 300 megahertz NMR is 10 ppm on a 600 megahertz NMR, okay? So in the case of things where you have the lower frequency or the lower ppm number, you have what is called more shielding, or we call that the shielded section. So basically, downfield, closer to 0, is shielded. And as we go higher and higher up to 10, that's de-shielded, okay? So those are the 2 directions here. But again, what I wanted to demonstrate here is that if we looked at a band that was a 50 megahertz NMR, that band would only be this big. So we'd have very hard time differentiating them, so that as we get to bigger, bigger fields, we should get cleaner and cleaner spectrum. Okay, so I just said that as we go to higher and higher frequencies, we should get cleaner and cleaner spectrum. So let me prove that with this demonstration here. So when I first came to school here, we actually had a 60 megahertz NMR. And so I actually used one here at Texas State. It was electromagnetic even, and it thumped. And so if we took just this little, we have 3 hydrogens here. 3 hydrogens on this compound. This is cyanoacrylate, okay? So, but those three hydrogens, none of them are equal because of where they are in space, okay? So that means that if we took the spectrum here, we'd have these split and overlapping with these split and overlapping with these split, and we get this kind of very messy kind of spectrum. It's like, I'm not really sure which is which. It just doesn't look right. If we took that and upped it to a 100 megahertz NMR, then we started getting that signal to spread out some. So that's great, is we're getting it to spread out some, but it's still not as clear as it could be. Okay, let's do 3 times the frequency, which should give us 3 times the frequency spread out, which means that we have a lot more time to get separation between a peak and the baseline, peak and baseline, peak and baseline. And what we see is that the spectrum gets cleaner and it gets easier to assign protons. So in this case here, they were actually able to assign the protons based on shift and or splitting. That the ones next to the cyano group were the most shielded of the set. And then these two, because they're not equal in space, because we don't have free rotation around that bond, that we ended up getting these as the most deshielded, these as the second most deshielded. Okay. And don't worry, you don't need to know that yet, but this is where we're heading. Okay, so we're looking at how those different things happen, and we'll be able to look at these splitting patterns and discern a little bit more as we go forward. Okay, so field effect is actually, most NMRs are 300 or above now, so we really don't see this kind of spectrum anymore. So it's kind of the golden age of NMR right now. Okay, so the other thing that can change our shift is the idea that we have a difference in the magnetic electronic field around a device based on its structure. Okay, so in the case of acetylene here, because we have a pi bond here and a pi bond here and a pi bond here and a pi bond here, so we have those 2 pi bonds and they're above and below that, so it actually creates an induced magnetic field in that linear direction. What that's going to do is that's going to change its shielding. So it's going to actually not be as deshielded as the case of benzene. Benzene is more deshielded because of the ability for it to create an electron cloud and actually have that electron cloud more easily aligned with the magnetic field. So this is actually going to be more deshielded or more at a higher ppm than acetylene, even though they both have double bonds. Okay, and that same is true for when we have something like a carbonyl. Because of that pi cloud, we can get alignment with the magnetic field and change its ability to be shifted. And it's all about having that alignment that will change whether it's shielded or deshielded. Okay. And what we'll see is consistently through our tables that eventually you'll be able to draw a conclusion as to whether or not it's aligning with that magnetic field based on where it shifts. But most of the time you just have to just assign the protons to the different systems. Okay, so that being said, we have expected places for things to be. Okay, so in the case of our aliphatics here, we consider those most shielded. It's a nonpolar bond with those protons. It's the most deshielded, and therefore it's closest to 0. Here's 0, here's our TMS. So most of our aliphatics rarely go above 2. Okay, we consider these our most shielded system, and therefore that is where they sit. Now, if we start getting substitution nearby, that can shift it a little bit, because whatever is substituting there can either donate electron density or absorb electron density and change the electronic structure around the nuclei. Now here's the alkyne. Even though it has pi bonds right here, it's actually lower than we expected for other pi bond systems. Notice alkenes and aromatics are way over here, okay? But because of that anisotropy, because it's a linear molecule, it's not as deshielded as other pi systems. Okay. So once we start substituting something on that same carbon as those hydrogens are, which is that alpha carbon, you can start adding and subtracting electron density. If it's a halogen, it'll do one thing. If it's an oxygen, it'll do another. Okay, but just the presence of having those electronegative atoms there shifts them to de-shielded and shifts them up to higher ppms. Now, if we dye substitute, the effect can be additive, not exactly additive, but they can complement each other, and therefore we can actually have this shift higher. And then the most extreme that we're going to show here, even though carboxylic acids are above this, is the aldehyde. Okay, so we have this right here, which has its own created magnetic field. We have an electron withdrawing group on this hydrogen, and we have a partially positive charge on that carbon. Therefore, it's shifted, it's de-shielded the most of this set, and therefore is the highest ppm range. Okay, so it's just showing you that's why they're trending in this way. Even though the table is going to be very specific about different things attached, I just wanted to generalize the shifting is all about that electrons being able to protect that nucleus of the hydrogen from the magnetic field. Okay, so if there is a general trend on this, then we should be able to predict where the peaks are by taking into account the different things that are added or subtracted from it. Okay, get your books out again. All right. In Appendix B here, you can actually calculate where you expect to find peaks based on what's attached to the different groups. Okay, so if we look at this table here and we look at table B1, let's look for a CH3 attached to this carbonyl group. Let's look for just that right there. And a CH3 attached to a carbonyl. You don't see it. Where is it? It's on one of these tables. Methyl proton. Where is it? I can't see it. The appendix A chart 1. Oh, so that CH3 is on appendix A chart 1 because there's nothing else attached to it. So appendix A is for mono-substituted. So we can get that one from appendix A. And the methyl group next to a carbonyl is going to give us a 2.1. So we expect it to be in the 2.1 range. Now, the benzene ring here, we can look at the table and say, okay, it's going to be up around 7 to 7.5, depending on what's attached to it. But now we have to look at this one here. Okay, that one there has 2 different groups attached to it. So we can calculate that using our appendix B here. And we're going to start with the idea that anything with 2 protons on it is going to start at 0.23. So we're going to start with 0.23 as our shift. And then we're going to say, okay, well, there's a benzene ring added to it. And so that's going to shift it up 1.83 ppm. So we have to do 1.23 plus 1.83. And then the other thing attached to it is an oxygen of a ester. And so that's the top one on this table here. And so that's an additional 3.1. So if we add 3.1 to the 0.23 to the 1.8, we predict the peak should be somewhere around 5.1, okay? Just by adding the 2 different groups together plus the native methylene itself, we're able to predict that that middle peak is actually that CH2 that has those 2 different things. So we can actually go through and individually pick between table A and appendix B here, where each of them should be, just their shifts, not their splits, just their shifts. Okay, So, and then of course the aromatics are on table B. So do you see how to use Appendix B when you have something with two things attached to it? Okay. So this is, go through this a couple times and you'll see that, and then if it's got just one hydrogen on it, or the methene, it's a different shift. So we have to do a different shift for that. So this is with two hydrogens on it, is on the first side, one hydrogen on it on the second side. But then we look at what the different groups are, and we add those together, and it creates our calculated shift. Okay. So, and that table is on the next slide, but of course we can't see it. Okay. So this will also extend to things that are in rings. And so on the next part of the table here, we can actually look at different parts in different rings, both open and unopened, mono hydrogen systems, other functional groups that you have next to isopropyl derivatives. So this will give you a good idea about where things should be if we were going to go ahead and predict our NMR spectrum just from calculation. Okay, and we might do that for part of our activity as well. Hint, hint. All right, questions on table B? Okay, so I'll give part of the homework. I'll actually have a couple of these so that you get the how to use it for both two hydrogens and one hydrogen, and with and without rings. Okay. All right. So this also extends to vinylic groups. Okay, so when we start going to things with double bonds and the hydrogens on there, this can get a little convoluted because typically they're not identical. And all three hydrogens on a monosubstituted alkene will actually show up at different places based on their shift. And we can do that calculation on Appendix D, which is also where we can predict where they should be. But then there's a lot of these other structures on this same appendix here that shows you where things might be on ring systems that are conjugated or aromatic, so that they have different shifts, and they're not necessarily easy to predict, which is why they're listed here as this is a good starting point to look for your system. Now, if you have that really good version of ChemDraw, it actually predicts these for you, but that's like $3,000, so most of us don't have that. Okay, and then of course there are another table within that same thing, helps you predict where things are on monosubstituted benzenes. Okay, so if you have a nitro group, it's going to shift your monosubstituted benzene. If you have fluorines, etc. Okay, and it'll also let you shift. It'll also tell you we can also calculate benzene shifts, but that's different. Okay. All right. Questions on shift. Shift is what gives us most information about what's attached to it. The next thing that gives us information is the spin-spin coupling. Okay. All right. Let's see, it shouldn't be, yeah, good. Okay, I'm gonna go ahead and start spin-spin coupling. Okay, so in spin-spin coupling, this gives us an idea about, okay, if this hydrogen is somewhere near this hydrogen, they are not the same, that means this hydrogen has a different relaxation than this hydrogen, and therefore the T2 changes because of this spin-spin coupling. Okay, so this is what we're looking for in that. And so when this one interacts with this one, we have a couple different things that happen. Okay, we get not only splitting, but we have a cascade of other long-range and short-range interactions. So for example, hydrogen will do a 2-bond, so from 1 bond, so they're attached to the same carbon, and that's one kind of splitting. The 3-bond is the most common we do, where they're on adjacent carbons. That's the most common kind of splitting we do. But there are longer range. And other spin-active nuclei, for example, fluorine, commonly spin couple across 4 or more bonds. Okay, so we'll start to see that when we have. Now, just within the hydrogen system, that coupling constant is usually 0 to 20 hertz, okay? Which means if we actually calculated out the distance in ppm and we're able to divide by the strength of the NMR, we could get that number of hertz of splitting in our coupling constant. Okay, so J is a coupling constant, and in proton NMR, we're going to worry about 2-bond coupling and 3-bond coupling, with 3-bond coupling being the most common we'll use. Okay? So there's a big table on these coupling constants, and if we look on that, it's, what is that? Table F, Appendix F. Okay, now the things they list in this table here, in this appendix, are what we call, there's 2 things. There's the typical coupling constant, and this is the AB coupling constant. And notice in the first system here, on this first page, this is a coupling constant for a 2-bond, okay? And it's typically between 12 and 15 hertz, but the full range is between 1 and 30 hertz. So you typically see it, you know, around 13 or 14. However, it can be shifted depending on what else is there. For example, if it's constrained in a ring, sometimes that coupling constant gets bigger, okay? Now, the rest of these coupling constants we'll see are 3-bond coupling constants because they are through that 3rd bond. Most of the rest of them are not geminal, okay? So we see that our coupling constants are actually smaller. That 3-bond coupling constant is smaller than the 2-bond coupling constant. And the typical ranges are given here. So doesn't mean they can't be, if they are in that possible range, that's true, but most of the time we're going to see them in their typical range. And notice these change a little bit for when we have rings, especially small fixed rings that can't change position, because the cyclohexane has a chair and boat, so it can flip back and forth. And so it has a couple different things it can do, but the smaller rings can't. And so you have a fixed cis or a fixed trans, and they have different coupling constants. Okay, so let's talk a little bit more about, now that we know what those coupling constants look like in our table, let's talk about how to use them. Okay, so the first and simplest one is when we have our J2, which is our coupling constant between the geminal. Oh, so these are vicinal, sorry. So the vicinals are J3, are 3 bonds, okay? And this is our simplest pattern observed when our change in frequency, which is that distance that this splitting is, divided by the coupling constant is greater than 8, okay? So it's most commonly observed that way. If it gets less than that, it's harder to discern. Okay. So the initial split at the top here, this is the coupling constant splitting these protons into this, and then the split here is that change in observed frequency. So let's go a little deeper, okay? So if our coupling constant, if our change in frequency divided by our coupling constant is less than 8, we start to see the peaks change shape, get closer together, and they start looking like the same peak, okay? So in the case of where we've dropped from 8 to 5, they're starting to look more like a pattern we'd see for a basically a single proton that's been split by 3 other protons. So it'd be a quartet. And then as that difference in frequency change and coupling constant gets different, for example, the coupling constant is getting bigger or the frequency is getting smaller, it starts looking like the same peak, okay? So that could be a problem. Now this doesn't happen for most of the time in there, but what we'll see it happen is especially when we start doing chiral compounds, where you'll be able to, these differences are going to be less than that 8. Okay. So that's just a general rule. You don't have to remember that, but when you start seeing weird kind of overlappings, wait, hold it, that should be 2 peaks, but it's only 1 peak. This is what's happening. Our coupling constant has gotten bigger, and therefore the difference in that system got smaller, and therefore we are starting to confuse 2 peaks together.
So, sorry for interrupting. I didn't understand why every hydrogen is giving 2 peaks. Like, can you see there are 2 hydrogen in the vicinal? So there are 2
In
peaks.
this one right here, yeah,
Yeah, these
1 hydrogen over here and 1 hydrogen over here.
two. But
And
every hydrogen has 2 peaks adjacent to each other.
well, if they were all equivalent and there were no hydrogen splitting it, you get 1 peak. This means you have 1 hydrogen here and 1 hydrogen here, and they're different than each other, and they only have 1 hydrogen. So these are splitting each other. So I have peak 1, peak 2, and the fact that they are in that configuration gives us the same coupling constant for those 2. So 1 is one of the hydrogen, 1 is the other hydrogen, and then these are splitting each other by the J. Does that make sense?
Okay.
So imagine this is hydrogen, and these are non-hydrogens over here somewhere. And our coupling constant between this is our J is equal to, I don't know, 2 hertz. Okay, so this has X and Y, and this has something else. So this one is shifted up this way because of deshielding. This one shifted that way. And this is splitting this one once with a coupling constant of this, and that gives us these 2 peaks. This is splitting this one once, which is by that same coupling constant, which is giving us that peak.
Oh,
okay. Okay?
Yeah.
We're going to do more of these, but that's, thank you for the clarification. Okay. So as we get to more complex situations, we have to start looking at what we call our multiplet way of doing things, which uses a Pascal's pyramid. Okay, so if we look at this system right here, now we don't just have 2 hydrogens, we still have a coupling constant related to a vicinal where we have hydrogens here and hydrogens here. So we have 2 different carbons, a total of 3 bonds with each of these, right? And what we've learned before is that this hydrogen is different than these hydrogens because of what they're attached to. Yeah. So that means that those hydrogens have different shifts, okay? So in this case, our hydrogen on the carbon next to these 2 oxygens is shifted higher than the hydrogens that are attached to this phenyl ring, okay? So that's the shift. That's the first separation we see, and that's the delta V, change in frequency or shift, okay? Now, the fact that they are now there, we now have to worry about, okay, so these are vicinal, so they're going to have a coupling constant of between 10 and 15 hertz, okay? Right, so that's our coupling constant. So that's the split between these 2 peaks right here. That's our J, okay? But now we have our multiplicity, okay? This is 1 hydrogen. Actually, let me go circle it here in red. This has 1 hydrogen, but it's being split by 2 hydrogens. Therefore, it's going to be 1 plus the 2 hydrogens, giving us 3 peaks, okay? And those hydrogens are equivalent. So they give 1 peak for that. Plus, it has 1 hydrogen it's being split by, giving us a peak here. Okay, now, if we look at this, the split here to here and the split here to here is that same J value of 10 to 15. Okay. It's our same coupling constant. But we have a different pattern. Why? Okay. So it all goes to our coupling constant. So if we think about it right here, if we just have that coupling constant, that's going to give us a split of, let's call it 10 hertz right here. And then because one's going to give us a split plus 10 hertz and or minus 10 hertz, one is going to give us a signal of one equivalent here. So this would be split evenly to 1 to give us our first split for our coupling constant. And then this one is going to split to give us 1 and 1 here. And this one is going to split to give us 1 and 1 here, giving us a total of 2, 1, and 1. So this accounts for the heights we see in the splitting pattern. The fact that when we have this splitting, it has split once for the first hydrogen and then second for the next. And so that's why we get the patterns we get, is those coupling constants are splitting and half of it is added, well, not half, but each of these, when we add up the different parts that are split, we get that multiplet system. So obviously the number of peaks is n, which is the number of adjacent non-equivalent protons to the hydrogen that we're splitting, is the multiplet, okay? And the amount they split is our coupling constant, okay? Now, that's just for a 1 and 2 system. How do we know how to do it for more complex systems? Well, in organic, we just taught you, well, these are common patterns, remember this, right? Well, there's actually a reason, okay? And we call it the Pascal's triangle, okay? So if we can think about it, when we have our Pascal's triangle and we don't have anything adjacent to it, so our coupling is basically 0, it doesn't split. We have one peak, okay? If we have something next to it that has a coupling constant of any value, let's call it 10, it's going to split that peak into 2 peaks, 5 up, 5 down, okay? So that tells you the split we get and the fact that it splits, giving us 2 peaks. What if you have other protons that also split? If they have the same they'll have the same coupling constant, we then go up and down, and we get that second pattern, that 1, 2, 1 pattern for our 2. So this Pascal's triangle is where we got those patterns that you remembered in organic. But the fact is we can actually calculate them and show what the intensity of each of these different peaks are. Okay, so a triplet is going to be a single peak that is split by 3 other non-equivalent protons to give us a pattern of 2 other non-equivalent protons, sorry, because it's n plus 0 because there's no adjacent things, so it is, n plus 1, n is 0 because there's no adjacent things, and 1 for the proton itself. So this is 1 adjacent carbon, splitting it into 2. This is 2 adjacent hydrogens, splitting it into 3. This is 3 adjacent hydrogens, splitting it into a quartet. And it's a 1, 3, 3, 1. Because this one at 2 splits out to give it 2, this gives it 1 for a total of 3. We see how that Pascal triangle works at giving us our relative intensities based on the number of hydrogens we have nearby. So this is the number of hydrogens, non-equivalent hydrogens, that are within the coupling distance, that 3 bonds. Okay. So if we have 4 non-equivalent hydrogens, we're going to end up with this 5 peaks, 5 equivalent hydrogens, we're going to end up with 6 peaks, et cetera, et cetera. Now notice the values here change. That peak on the outside is always 1. So that peak on the outside will always be 1. So you're going to see this pattern where it'll always go diminish from the inside out. And it can be odd or even depending on whether or not you have this. So again, an even number will give you an odd number of peaks. An odd number will give you an even number of peaks. One hydrogen affects the other and split. Okay, non-equivalent hydrogens within the 3-bond zone will split that hydrogen. So this is the number of non-equivalent hydrogens. You get 1 for the hydrogen itself plus all of the non-equivalent hydrogens within 3 bonds. That's how many times it splits. Okay? There was a question in the super chat. Okay. So that being said, you can say that these are always going to be evenly spaced, and that even spacing is always going to be associated with the coupling constant associated with it. Okay. Questions on it? Okay. So when you're looking at this, you can actually take the ppm distance there and convert it from that to using the power of the NMR to get your coupling constant. And you can see that the coupling constants are the same. Now, occasionally you'll get an odd pattern. What that means is that you have 2 different competing factors with 2 different coupling constants. All right. So, moving on, let's go ahead and look at the effect of field strength on the order of spectrum. The order of spectrum is associated with having your coupling constants be equivalent enough that they line up correctly, okay? So in this case here, we have a simple system where we only have 2 types of hydrogens right here, okay? We have these that are attached to the ones with the oxygen. We have these that are attached to the ones with the chlorine, so that those are 2 different. So we should see 2 peaks, okay? And they each have 2, so we have the methylene itself plus 2 hydrogens, so they should each have 3 peaks. If we looked at an 80 megahertz NMR, okay, because those things, the coupling constants are around 15 or 10, we only have an 80 megahertz NMR, and so our coupling constants are overlapping and muddling the system. We cannot get a full separation of peak to baseline. When we can't get a full separation of peak to baseline, we end up getting these, you know, kind of mushy additive effects. Okay. If we go up to 100 megahertz NMR, right here, or if we go up to 100 megahertz NMR right here, we start seeing differentiation here. But what we're probably seeing is that it's not exactly the pattern we were expecting. We were expecting 2 triplets because we have 1 shifted upfield, 1 shifted downfield, and we have 2 non-equivalent hydrogens on an adjacent carbon. Therefore, we're expecting 2 triplets, okay? Now, if we go up to a 300 megahertz NMR, and basically we're spreading that signal out over a greater distance, so we have more time for the peaks to come all the way back down to 0 in our time domain. When we do that, we start to see the peak we're expecting, that 1, 2, 1 triplet we're expecting. Notice there's a slight shift on that right here, that these are slightly off here. Probably something to do with the CHEM of the N. Okay, so the more you can, the wider the frequency of NMR you have, the more this spreads out, the cleaner spectrums you get. But we can still go back calculate the distance here and the distance here from ppm and back calculate to figure out what our coupling constant is. Okay, so how close, yeah, we can get to this. Okay, so when we're talking about this, we want to look at a way to describe what our multiplets should be based on what we see, okay? And so the system we use here is what we call the Poppel notation. So in Poppel notation, you're going to look at the hydrogens that you're looking at, the hydrogens that are close enough to actually split, okay? So the hydrogens you're looking at are going to be your A hydrogens, and you're going to denote how many hydrogens are there by the number below it. So the A is the atom you're looking at, okay? The number on it is the number of hydrogens on that atom, okay? Then the next thing over is your M. This is close enough that it will split in a normal 3-bond splitting, okay? So those are the ones you want to see. And then the next one over is one that should be far enough away to not do our first order splitting, not have a coupling constant big enough to see in our splitting pattern, okay? So, and that also shows this. So these 3 hydrogens are this, 2 are here, and 3 are here. So in theory, these right here should not split this because they're too far away, okay? So when we apply that to actual spectrum here, we can say that we have one system here, and they are only going to be interacted with these. Okay, now these right here are far enough away from these to not be interacted, so we shouldn't see any effect by those. However, we will see an interaction with these. So that means this peak here should be affected by 2 protons to give us a total of 3. Okay. This peak here is going to be interacted by 2 protons to give us a total of 3, because these are equivalent protons. Okay. This right here is interacted by 3 and interacted by 2 for a total of 6 peaks. Okay. That's why you use the Pople notation, so you'll know exactly how many peaks you should see for each of the things. I thought protons within 3 bonds would affect the hydrogen on the end. Right, it's protons within 3 bonds. So if we have the C, H, it's the 3 bonds from hydrogen to hydrogen. So that means this is our X carbon over here. This hydrogen is 1, 2, 3, 4 bonds away. This hydrogen is too far away. So this is 4 bonds away, this is 3 bonds away. And these are 1 bond away and identical, so they only make sense, okay? Okay, so that's what the notation gives us, is it tells us which ones are close enough to have an effect, okay? So that means that the methyl group here, now the methyl group should be shifted, it should be the most shielded because there's nothing else attached to it. So it should be the closest to 0, and it should have 3 peaks, okay? This one right here has a methyl group and something, and well, let's do the X here. This has an electron in a drawing group. It's going to de-shield it. So that means it's going to be shifted upfield, and it's going to have 3 peaks, which is what we see here. And this is going to be intermediate between the two. One's not shifting, one is shifted upfield. So it's going to be somewhere in the middle. It's going to have a total of 6 peaks. We have 1, 2, 3, 4, 5, 6. Yeah, and we have 6 peaks. And this is a blow up of these. Notice these blow ups actually are done not in ppm, but they're done in hertz, okay? Which means if we took the peak to peak distance here, we can calculate these two should be identical, and that's the coupling constant associated between, let me use a different color. The coupling constant between these hydrogens and these hydrogens is JAM. This is JAM. Okay. The coupling constant between M and X is the one between these two atoms here. This is JMX. And this right here should be a J. This is kind of the combination of the two. And if it's close enough to the same number, we get the exact same peak. If it's not close enough to the same number, it starts to broaden out and get weird. But because they're all hydrogens on carbons, they should be fairly close to that, 10 to 15 hertz range. And it looks like it's, the difference here is about 9 hertz. If we look from here to here, it looks about 9 hertz. So that's our coupling constant. All right, questions on Pascal's triangle leading us to the Poppel. Poppel also is based on that same idea, but it clarifies which hydrogens can be split and how many times they should be split. Okay, so it's not a guessing game. You're actually noting things such that you can make sure you are not, you're only going 3 bonds. You're not going 4 bonds. Okay, let's see. I think, okay, yeah, let's do one more. Okay, and so we're going to apply that same thing to the aliphatics here. We're not going to do the benzene ring here because that's actually more complicated. We're going to do that in a little bit. But what I want to do is look at these two right here. So in our Poppel notation, we would have, this is our A, and it has 3. And this would be our M because it's attached to it, and it has 2. Okay, so given that notation, we're expecting A to have 1 plus 2 or 3 peaks. We're expecting M to have 1 plus 3 or 4 peaks. Okay, so that being said, we're expecting the methyl group to be the furthest upfield because it's most like that. And because we have something with electron density there, it's going to shift it downfield. And so what we should see is 4 peaks downfield from 3 peaks. So let's look at our system here. You can't quite tell there are 3 peaks there. You can't quite tell there are 4 peaks here, but we've blown it up. And if we look at the, right here, this is about 7 hertz as a coupling constant. And this looks about 7 hertz as well. Right here. So this is our uphill one with our 3 peaks as predicted. And this is our downfield one with 4 peaks as predicted. Okay? So again, this is first order. We can go to further spin, and we are not going to talk about that until we do the other pulse sequences and 2D NMR. Because when we do that, we're actually looking for second order, third order, and fourth order. You can actually do an experiment where you're only looking at protons 3 bonds away, or 4 bonds away, 5 bonds away. But the way the pulse sequence is set up for proton NMR, we should see only these, the 2 bond coupling constants, the 2 bond splitting, and the 3 bond splitting. Okay, let's see. We have, all right, let's do one last one, and then I'll end here. Okay. So in this case here, if we use our same Poppel notation, this carbon right here, we don't worry about because it doesn't have any hydrogens on it. So, well, actually it does. So this will be our, let's see, this is going to be our A, is going to be this one right here. And this is our M because it's attached to it. And this is equivalent. So this is also an A. So what we're going to say in our Poppel notation is we have an A6M1 because there's 1 hydrogen attached to here, but there's 2 A positions that are equivalent, and therefore it's an A6M1. Therefore, our A is probably going to be most downfield, closest to 0, and it's going to be split by only 1 proton, giving us 2 peaks. So A should have 2 peaks because the thing next to it only has 1 hydrogen on it. Now M should have 1 plus 6 protons, or a total of 7 peaks. Okay, and it should be shifted upfield from where our methyl group is. So let's take a look at that. This is the benzene ring. We're not going to worry about that. But under our Poppel notation here, we have 2. We see a perfect split of 2 protons right here. And we get our coupling constant somewhere around, maybe 7 hertz right here. And then we have 1, 2, 3, 4, 5, 6, 7 peaks for our other peak. Okay. Now, notice this is really small if we look at it here. And if we integrate that, that's to 1 hydrogen. That's integrated to 6 hydrogens, and that's integrated to 5 hydrogens. So that big doublet right here kind of overshadows the other two peaks, but when we blow them up and do them on the Hertz scale, we can figure out what our coupling constant was. And by doing our Poppel notation, we know exactly how many peaks we should have. Okay? Questions on this splitting technique and or Pascal's triangle. Notice that these right here, these are going to be our value of 1, and this is probably going to be somewhere in a value of 50. Right here, if you go back and look at your Pascal, right there, the difference between those is on that Pascal triangle. Okay, did I run late? I'm supposed to stop. Yeah, okay. So, all right, well, thank you very much. If you want to hang out and have a answer a question, I can do that. Let me go ahead and stop recording.